Hey, welcome to my talk about summer. I've spent before a day or two on the topic of type analysis improvements. So I will just quickly introduce myself. My name is KAREL HÁJEK. I'm a second year computer science student at Brno University of Technology, and I just like to know how things really work, which is the reason why I got into reverse engineering. I'll shortly explain what the Google Summer of Code is. It's an annual event organized by Google to get students into open source. And you pretty much work for an open source organization during summer break, which in my case was Radar 2. Headline of my project was type analysis improvements, but the first month I was working on getting type information out of Dwarf and PDB debugging formats, and I kind of stuck with them. So in the end, most of my work was done especially on the Dwarf and PDB, and some also on the Itanium vtables and RTTI runtime type information. I actually started to work on the type analysis on the very end, but I didn't have results yet when I was making these slides, so yeah, it's not part of the talk. So let me just start with the work I've done, the Dwarf debugging format. So the main goal was to load the type information, and there were a couple of challenges. The state of the Dwarf codebase was unknown, as it wasn't really touched since it was written like 6 years ago. And after digging a bit, I found out a lot of the parsing didn't really work. The information that I needed to process the type information wasn't parsed out, and was especially confusing as I didn't know Dwarf well, and it took a bit of reading to get into, because Dwarf is quite complex and has many standard versions. For example, Dwarf 2 has about 100 pages, and the fifth version, Dwarf 5, has about 500. So it grew every version. And I was a bit confused because I didn't know where to start. So yeah, I started writing tests. They helped me out a lot to find the problems in the current implementation and getting familiar and comfortable with the code base and also the Dwarf format. Once I started fixing the bugs and knowing the code, I started extending the parsing necessary for the types. So I've added parsing of the debug info section and support for the different Dwarf versions. Once I got that, I started to actually process the type information. Here's an example how the raw Dwarf looks. This is the debug info section, and here you can see you have different entries. Each entry has some tag and some attributes. Every entry is a node in a tree, and each node can have a children, just like a tree. So for example, a structure type has member children, and also the subprogram, which is some member method, I guess. So if we find the tag that's interesting to us, so for example structure type and enum type, etc., we can travel the attributes and the children to reconstruct the type. So yeah, that's what we do. We take the name of the structure, we get the size in bytes, and then we get the members. So we can see its name is mystruct, and it has a member A. The member has an offset inside the structure, which is 0, as it's a first member, and it has a type. The type is an offset to another entry in the section, which is 6e, and it's here. And if we travel all the type entries until we can't travel anymore, we get the whole type. So in this case, if we go to 6e, we can see it's a volatile modifier, and it's modifying the type 6.8. 6.8 is a pointer, so it's a volatile pointer pointing to 7a, pointing to const modifier of 7.3, and that's an unsigned character. So the result is volatile pointer to const unsigned character. And that's pretty much what we're doing. We're just traveling all the entries, reconstructing the whole types, and for each type attribute, we recursively travel all the entries until we get the complete type. This type information is processed after the dwarf is parsed, so by default it's automatically when you open the binary with dwarf information. I've tried to emulate the C syntax as much as I could when doing the parsing, which doesn't do justice to different languages like Go, for example. So yeah, here's an example. On the right you can see C++ source code, on the left you can see output of Radar after opening a binary or this source code compiled with, of course, dwarf information. Here you can see the member A I've described earlier. So A is a volatile pointer to constant and character. And the result here in Radar is exactly the same. I'm just missing a space here, but that's not a problem of the parsing or the processing. We can also parse enums, arrays, multi-dimensional arrays. We can do references, array value references, etc. I've even tried to do correct C declaration of function pointers. I think I've kind of succeeded with it. I'm only missing arguments, but yeah, that's a to-do. In the SDB, it looks about like this. You just have a structure, a list of the members, the whole size of the structure in bits, and then each member has a type and offset inside the structure. After the types, or yeah, that was all to the types. Now let's go to the function information. So another thing, yeah, I've also added integration of the function information. So we can load a function address, function signature, get the variable and argument information with their location. We now support every location that we can represent in Radar, so base pointer based locations, stack pointer based locations, and register based locations. And we also create flag for global variables. Everything from functions is processed at the same time like the types are, but to actually apply the information you need to use AAA. Here's an example. Again, a raw dwarf information, so you have a subprogram entry which describes some function, and you have a name. Again, you have a name and some other attributes like a function address, a region type. Then it also has a children. The children have, again, name and type, just like the members of the structure. It has a location which is a dwarf expression that describes the location inside the binary. For example, this problem means it's some offset from a certain register, maybe base pointer register. If you look, one more side note, everything is saved into dwarf namespace in SDB inside analysis. Here we can see what's parsed out of the raw information. We get the function address, name, the signature. We can see the main has no argument, and all the list of all the variables with their location and the type. B means it's a base pointer based location, and this is the offset from the base pointer. So with all the function information and the type information, we can get pretty nice results into this assembly. Again, next example. We have a function main, we have the signature as a comment. The reason why it's a comment is because not all languages are C, so not all declaration will be compatible with the C parser that we use to apply signatures, function signatures. So it's just a comment. Here you can see all the variables are named based on the dwarf information, the same with the type, and in the source code you can see the names are substituted, name of the variables are substituted, so you can nicely see what is what, and it's very easy to read. Yeah, one more example, we're also creating flags for global. So for example, if you have a location that's an address, like here, if you have a variable that has a fixed address location, it's probably a global. And if it's under a function, a scope, it's probably some static variable. So we're creating a flag for those. Another example, we have a signature here. It's more complex. Finally, we have some arguments. We can see the arguments have a location. They're immediately copied on the stack. It's all loaded from the dwarf. And we also have the flag set for the global here. So yeah, that was all I had for dwarf. Um, there's a lot of things that can be done. A lot more testing. I'm sure the implementation has many bugs because it's a little complex. We also need to support new things from Dwarf 5 because it introduced a lot of new things that we cannot use. Also support for Dwarf in a different file from the binary in a separate file is important. Adding more dwarf register mappings so you can get the location of the variables, parsing of additional sections, optimizations, and just generally getting and applying more information you can find into dwarf. So if you have any ideas, if you find any problems, any seg faults, just make a GitHub issue or just ping me on Telegram and I'll have a look. PDB, so work on PDB was pretty much the same like on dwarf, except I didn't do any function information. So it's just like the dwarf, but just the types. Again, we parse out the types and save them into SDB, just like with the dwarf. I've also fixed some bugs I found, added some tests, and refactored a lot of the code. But only new functionality is the type one. Last thing I worked on was vtables and runtime type information. I've changed some vtable heuristics, like that the vtable RTTI pointer doesn't have to point to the same section because sometimes it is in different data section. I've added a fallback option to RTTI parsing because we are depending on symbols that will tell us what the type info is. What type info it is. There are three options. It's either a base class or a single inheritance or a multiple inheritance. Now if there is no symbol that would tell us, we just try to parse as much of the input as it makes sense, and based on what we read, we create the appropriate type info class. Also, if you use AVRR, you get loaded all the inheritance information founded in the RTTI. So if you print ACL, you can see all the inheritance loaded. I've also added an ASCII inheritance graph to visualize the class structure and the inheritance structure. So yeah, thanks. That's all from me. I would like to thank Google and Radar for the opportunity, and the Radar dev team for all the help, especially Xpilka for mentoring. And yeah, I hope I can stick around for a bit longer and finish my to-dos. So that's all from me, and enjoy the rest of the R2Con.